Sorry.
STMicroelectronics. He's based here in Santa Clara, and he leads the development of MEMS devices, and he'll be obviously talking all about that today, but for many different applications, consumer, automotive, industrial applications. Prior to ST, he was a senior director of MEMS technology at CSR, where he worked on the integration of MEMS sensors, GPS, and wireless technologies. He was a founder and CTO of, I probably will mispronounce this, Actuator.
Yeah.
Okay. Yeah, Actuator, where he pioneered the use of GPS and MEMS sensors in vehicle safety applications. And he's also, of course, worked on a variety of other advanced navigation technologies, including at Visteon and autonomous vehicles at the corporate R&D center at Caterpillar. So that's interesting in the agricultural field. So he's also a control system scientist, has been at Thomas Jefferson National Accelerator Facility. And also he received his Ph.D. from William & Mary, and he has been an adjunct professor at the Indian Institute of Technology in Delhi. So let's welcome him to bsac.
Thank you, Jonathan, for the introduction. So I'm Mahesh Chowdhary. I'll be talking about intelligent MEMS sensors with on-sensor machine learning, tiny machine learning, I should say. So here is the outline of the talk. So I'll start with intelligent sensors, their past, their present, and some ideas about their future. Then I'll start to talk about on-sensor machine learning with a solution that we call as machine learning core. Next, I'll talk about the AutoML, auto machine learning for this aspect of machine learning that's available inside our sensors. And lastly, I'll talk about the flexibility that a new generation of sensors that we're putting together, which we call them as ISPU, Intelligent Sensor Processing Unit, what they provide. I'll conclude with a summary. So, the activity in area of MEMS devices, MEMS sensors, it's not new. You probably might know this, but there was an invention back in early 60s where a resonant gate transistor was used for frequency filter for ICs, and this was a MEMS device. So there's a patent for this, that you can still search and see. Now, the commercial utilization of these devices, started in early 2000s. So the very first device that I'd like to talk about here is Nintendo Wii. So Nintendo Wii essentially is the device that used an accelerometer from ST, and it was used to detect, swinging, shaking, tilting of the game controller. It became a pretty popular device at that time. It had all kinds of interesting games. Then in 2007, the very first full touchscreen smartphone. This, you can guess it's an iPhone. It used ST's accelerometer to do something fairly simple, which is to detect portrait versus landscape mode. So you look at the gravity vector and make a determination to orient the screen in the portrait or landscape mode. Then in 2008, again, the same company, Nintendo, they added gyroscope because they realized that if you add a gyro, you can deal with more complex motions and improve the user experience. So that's how, this story started, which is where, you see intelligence, being utilized through logic running on a microcontroller. So the early sensors, the main idea was you have a MEMS sensing element, you have an ASIC for signal conditioning, some data processing and data acquisition. And most of the intelligence in these scenarios would live on a microcontroller or an application processor. So in case of this device, like a smartphone, it would be the application processor. In case of a gaming controller, that would be a microcontroller. And as some of the algorithms that they were using, matured, you can see that many of these algorithms started to get embedded into the sensor. And the very first ones were things like pedometer. So step counting, once that algorithm is mature on a microcontroller, then you put that into the ASIC on the sensor. Significant motion detection, wake up, if you pick up a device and it should wake up the device to do something, that action, all of that logic started to get into the sensor. So free fall detection, 60 orientation, those kind of features. One of the other roles that these sensors, accelerometers and gyroscopes played was to embed sensor fusion, into the sensor itself. You want to determine 3D orientation of a device, like a gaming controller, for example. You want to know in three-dimensional space, roll, pitch, and yaw angles. So as the algorithm matured, they started to get embedded into the sensor. I'm specifically going to talk about ST sensors, but many of these things you can find in other sensors that are commercially available. So instead of giving a raw accelerometer or gyroscope as an output, sensor produced Euler angles, roll, pitch, and yaw, or quaternion, which essentially reduced compute on a microcontroller, and you could directly use that in your application. The next thing that ST added in our sensors was finite state machine. So the intelligent sensors, this is now I'm talking about 2011, 2012. Finite state machine was added into the sensor. So finite state machine will traverse through different states. You can design your finite state machine to traverse through different states, and ultimately you take some action. So if you're looking at acceleration data, and let's say you want to do face up or face down for a mobile phone, this can be accomplished by a finite state machine. You would look at your gravity vector and make a determination that, okay, now the state is face up, or now I look at it and the state is face down. The next development in this journey was machine learning core. So machine learning core essentially can run machine learning algorithms on sensors and a decision tree. So I'll talk more about what it can do. So this was now about 7 years ago, 6-7 years ago. That's when it was added into the sensors, and it became commercially available for a variety of applications. So I'll talk about a few of these applications in the presentation. There are two different paradigms when you look at sensors and use of sensor data. So one of the paradigms is that you would send out raw sensor data for an extensive compute on the cloud. And in this case, as you can imagine, you have possibility to archive large amounts of data. You can run all kinds of algorithms on that data. You can have as much compute as you want to. And once that computation is done, you can generate the result and send this back to the device. Now, this model has some advantages, but many disadvantages. This model, the biggest disadvantage is time-sensitive applications. You cannot deal with the latency because you need to send the data to cloud, compute something, send this data back down to the device for user to take some action with it. So that's why now the paradigm has changed. It has shifted. So all of the compute now is moving towards edge. So for sensors which have compute in them, we call them edge of the edge, because now the logic does not run in a microcontroller or an application processor. It runs inside the sensor. So sensor is essentially edge of the edge. So the primary reason for that is you would essentially, for applications that cannot deal with latency because of the user experience, they would need to run the logic in the sensor or the microcontroller. Many applications, they do not have network connectivity all the time. So in that case, you do need to run those algorithms on the sensor. There are some applications where you do not want to send this data across. The data should not even leave the device. In some cases, data should not leave the sensor for privacy reasons or for whatever reasons they may be. In those cases, logic inside the sensor makes all the sense. So that's where machine learning core comes in. So machine learning core, to describe that as a block diagram here, essentially it has a sensing element. We have IMUs and accelerometers, inclinometers, they come with machine learning core. So in case of IMU, you have an accelerometer and a gyroscope. Then you have a signal conditioning block. So I'm describing to you the finite state machine first, and then I'll go into machine learning core. So in case of finite state machine, you would do some signal conditioning. So you could apply a filter on the sensor data inside the sensor. So you can apply a low pass filter, high pass, band pass, notch filter, whatever it may be based on your application. And you could also do some conversion of the data. So sensitivities, all those things that can be applied. Next comes the finite state machine block. So it will basically process the filtered data through the finite state machine logic. It has two portions to it. There's a data section, and then there is an instruction section. So instruction section will contain your different states. So just to give you a flavor of finite state machine, I can use a typical example that of a person driving their car, parking their car in a parking garage, getting out of the car and walking away from the car. So it can be described by different states. So one of the states that you can detect using an accelerometer is the person is driving the car. The motion pattern for a car is distinguished, it can be distinguished from other motion patterns. So that's number one state. Next state is that you stop the car. So again, accelerometer pattern can tell you that, okay, now car is stationary. Third one is, let's say the device is a mobile phone. So if the person gets out of the car, which means the person will stand up and start to walk. So getting out of the car can also be detected. That's a motion pattern that you can detect in the acceleration signal. And finally, walking. So here you see four states: driving, car is stationary, person gets out of the car, and then person starts to walk. So a finite state machine can do this. You look at the acceleration pattern and do this. So finite state machine is one implementation that's available in the sensor, and the next one is machine learning core. So in case of machine learning core, again, you have sensor data that is available to you, which is accelerometer or gyroscope. Most of our sensors, they have capability to bring in external sensor data. So you can connect a magnetometer to the auxiliary port of the sensor. So it'll be an I2C or I3C or a SPI port, where you can bring in the sensor data into the machine learning core. So magnetometer, pressure sensor, or any other such sensor like time of flight, to give you proximity, all of those. So this sensor data then can be processed through the computational block, where you can, again, apply filters to the sensor data. And as you know, any of the machine learning algorithms, they will operate on features. So these features can be, mean, variance, so on and so forth. You design your algorithm with certain features. So that's the next piece. That's the next block. So in the computational block, you apply filters and compute features. Then you pass on this signal to a decision tree. So decision tree essentially, consists of nodes. These are connected nodes, and each node can do if, then, and else condition on features that have been computed for the given signal. I'll talk more about it. So the idea here is this is what machine learning code looks like in a sensor. So something very quick. So finite state machine, as I described again earlier, it will operate on different states. And you can traverse through the different states by putting in logic, like, looking at thresholds. If A happens, does B happen? If A and B have happened, does C happen? Those kind of things. In case of machine learning core, it is primarily a decision tree logic, where each configurable node, will execute if, then, and else condition. And this generally is built through offline analysis. So as any machine learning algorithm, you'll collect lots of labeled data, and then you put this together. So machine learning algorithm, the decision tree that we used, falls under the category of supervised machine learning, and amongst other all the different methods that you generally apply. And our 6-axis IMUs, accelerometers, and inclinometers have this. So now diving deeper into it, we talked about the sensor block, we talked about the computational block, and we talked about the decision tree. A couple of things I want to further add is these sensors come, besides the decision tree, they come with a meta classifier block as well. So as you know, if you want to smooth the output from a decision tree, you can use a meta classifier. And the whole idea here is that, imagine the case where you're detecting this scenario of person driving the car, person parking the car, person getting out of the car and starting to walk. When the transition happens, if the algorithm essentially is not able to distinguish between two different states properly, your output would flicker, stationary versus moving. So if you put a meta classifier with some logic in it, you smooth the output. So for the sensor data, the input that is available in the sensor data block is you can give accelerometer data as any of the axes, AX, AY, AZ. You can provide norm or norm squared. Same thing for gyroscope. If you bring in an external sensor like a magnetic sensor, same thing. You'll give field strength for each of the axes, norm squared of that, or norm. Now, next block is this computational block, which consists of filters. So, here is a expression for the second order IIR filter. So it has the sensor now has the capability to run this second order IIR filter. And if you can basically design your own filter based on your use case, where you would specify these coefficients, A's and B's and the gain, you can pretty much create any filter you would like, whether it is a band pass, high pass, low pass, notch filter, whatever it may be. And you can apply this filter on any of the inputs. So let's say, and it can be a combination. So let's say, your algorithm needs variance or norm of the accelerometer. You can apply, let's say, a low pass filter that you have designed. This block essentially will process that, input signal, which is norm of accelerometer, and provide the filtered signal to the computational block, either in the decision tree or in the finite state machine. You could use a combination, norm of accelerometer, z-axis of gyroscope. It's possible. Then comes the computational block where you compute the features. So, what we have are most commonly used features in any algorithm that you want to design. So mean, variance, energy in the band, which is, as you can imagine, it's a poor man's FFT, peak-to-peak value, zero crossings. Again, there are two flavors to it. You can also count positive zero crossings or negative zero crossings. Then you have peak detector. So you can count positive, you can look at positive peaks and you can look at negative peaks. You can look at maxima, minima, all of these. So there are 31 features that are available in this sensor. So as you can imagine, this logic will work on a window of the data, right? You would, if you're sampling the sensor data, let's say at 60 Hertz, you would have 60 samples in 1 second window. So you would compute mean or variance, energy in the band, whatever it may be, on that specific window. Now, different sensors that we have essentially have different capabilities. The commercially available sensor LSM6DSRX, it has a capability to run 8 decision trees at the same time. And it has capability to run a decision tree combination with 512 nodes. So just to give you an idea, if you want to develop a human activity recognition algorithm that uses inertial sensor data, a decision tree with about 60 to 70 nodes will do a very good job, 96% or better accuracy. So what does that mean? It means that you have plenty of space to put other logic and you can run different applications on that same sensor. So you can run up to 8 different decision trees at the same time. A decision tree to detect motion versus no motion, that'll be like 4 nodes. So in 4 nodes, you can determine, is there significant motion to pick up? The last one is an accelerometer only, LIS2DUXS12. So it essentially can run 4 decision trees at the same time. This is an ultra low power accelerometer, and it can, have 128 nodes available to you for decision tree. And everything has a meta classifier, and you have specific registers out of which you can read the results, or the sensor will generate an interrupt for the application processor. So the key steps that anybody who wants to build a solution using machine learning code would follow are these 5 steps. So the very first step would be to capture data. So I'll use the example of human activity recognition. So, here, you can use either a smartphone, or you can use a smartwatch, or you could use one of our HDKs. We call it a sensor tile. It's a tiny device that you can strap onto your wrist. It has SD card on it, and it has Bluetooth connectivity. So you can use that device to collect data for walking, running, jogging, bicycling, whatever it may be. Then the next step is to label the data. pre-process this data. You would do feature engineering next. In feature engineering here, you would pick what features to select. Just to give you an idea, if you want to detect significant motion, variance is enough. So variance above a certain threshold will tell you that, okay, device is moving, and variance, and if the output is below that certain threshold, device is stationary. So you can do your feature engineering. And next step would be to build your decision tree. So to build the decision tree, there are many solutions that are available online. We have a product called as MEMS Studio, which I'll talk about briefly. That also gives you your decision tree. Once that decision tree, along with its performance statistics, has been generated, then you would embed that into the solution that you're building. So MEMS Studio essentially can do all of these, and you can work with Veka, you can work with MATLAB, you can work with Scikit, or you can use Python, whatever it may be. And essentially, it'll generate the decision tree for you along with the statistics. Statistics would be, what's your absolute accuracy for the given training data set? What is, the essentially overlap between two different classes that you have selected. So all of that is, these tools produce all of that. We have ST's own logic that's embedded inside MEMS Studio, so you can use ST's own decision tree generation algorithm. If you take the example of, again, human activity recognition, the very first thing that you would do if you want to build a solution is to define your classes. So your classes can be, stationary or walking or running or jogging, bicycling, whatever it may be. If you have availability of magnetometer, you can do something more than what you can do with just accelerometer and gyro. So you can do, something more when you use combination of accelerometer, gyroscope, magnetometer when you add a pressure sensor, because z-axis will give you pressure sensor will give you z-axis, which is your altitude information, or change in your ambient pressure, which essentially which essentially can tell you many things about your context. So the first step is to define those classes, and next step is to all the data that you have collected to clean and label that data, pre-process that data, make sure that the cleaner the data, more properly labeled the data it is, the more accurate will be the output from your decision tree that has been generated. So next step is features. Feature engineering is important because you have to pick those features. There are 31 features that are available to you in the sensor. So you have to pick the right features, and generate the decision tree. Because that if then an else condition for each of those nodes in the decision tree, if you use the right combination of features, you will achieve greater coverage, which means that, let's say you collected the data using 20 users, it should work for the rest of the population. The idea here is pick the right features and thereby achieve the best possible performance in real world implementation. Now, once the decision tree has been generated, then comes the step of integrating that into your actual device. Actual device would use some firmware. So decision tree becomes part of your header file, which essentially now is processed. You read that decision tree. Your logic would then download that into the sensor over the serial interface, which is I2C, SPI, or I3C. I'll talk about some applications. So, what I have picked here are some applications that pertain to computing device. So all of us use, these devices, laptops. One of the applications that has been enabled by this sensor, and it's actually in production for past 4 or 5 years, is detecting in bag and out of bag using an IMU. Actually, you just need accelerometer. So in-bag detection algorithm will detect, if the laptop essentially is in the bag. And to run this decision tree in the sensor, it will take only 37 microamps of current consumption. So look at the number here. If you were to implement this logic, I'll show you a comparison when you run the logic on a microcontroller or an application processor. Out of bag, so essentially, this kind of application is useful. This kind of feature is useful when you take a laptop out of the bag, and you are you want the user experience to be good, which means that laptop should be ready for you to log in. So out of bag detection, on table detection. So on table versus not on table. This can be done by a decision tree running inside the sensor. The reason why this is important feature is if the laptop is in your lap, you want to control the radiation profile, and you want to control the thermal profile of the laptop. Some of the gaming laptops, they can generate a lot of heat. Same thing for, all of the radios that you have on your laptop. So on table, not on table, 14 microns of current consumption for the algorithm running inside the sensor. Pickup, if you picked up a laptop for automatic wake up, it will work for your laptop with 5 microns of current consumption for the compute when it is running inside the sensor. So we have a whole bunch of these applications and demos that are available on GitHub. For industrial applications, we have put example for status of the drilling machine. Is the drilling machine stationary? Is somebody holding it, or is it being used to drill into something? Static inclinometer, human activity recognition, gym activity recognition. It'll detect different types of exercises, lateral, squats, bicep curls, all those kind of activities. For vehicle monitoring, in case of automobile applications, this is an example that's available on GitHub. To detect vehicle is stationary or vehicle is moving, to detect if somebody is jacking up the car to steal the wheels, or is the car being towed away, or is something bumped into your car. It can be done all by this algorithm that runs inside the sensors in a decision tree. So, to talk a little bit more about this in-bag detection, so it is implemented using 2 pieces. There are 3 different decision trees that run at the same time in the sensor. And there's a finite state machine that combines the output from these different decision trees. It will work for all these scenarios. If the person is, you put the laptop in your bag, it'll detect it when the person is walking, running, for different transportation mode. The person can be on their bicycle, they can be in the car, or they could be in a bus or train. And also, of course, works for stationary conditions. So it consumes only 37 microamps of current. So laptop's main processor, or even if they have an embedded controller that works with the sensor, can be off, and in-bag detection logic can work. But the reason why this algorithm has been put together is to prevent overheating of the laptop. When many times you might have experienced this, that you put the laptop in the bag, the laptop does not go into standby or hibernate mode, and it'll drain your battery. So one of the important aspects here is that it enables sustainable consumer electronics development. And how we did this math. If your laptop does not go into standby mode when the lid is closed, and battery drains overnight, and let's imagine the case where it happens once a quarter. So it drained for 8 hours. It might take 8 hours to drain, so it drains the battery. So if you compute that, if all the laptops that are available in the world, so about 260 million units that are available in 2023, and you would have saved 70,000 tons of CO2 emission just by this aspect. So there are many laptops that are now commercially available, which have this feature driven by the logic running inside the sensor. Now this is the current consumption that I wanted to show you. So let's say I implement human activity recognition, and I run this inside the sensor. And I can also run that same algorithm on a microcontroller. I would be transferring the raw sensor data to a microcontroller. So on the left-hand side here, what you see is the computation for a microcontroller. So LSM60SOX sensor, when you have the sensor configured to be sampled at 26 hertz in low power mode, it'll consume 15 microamps of current. So in this particular case, we are using a Cortex-M4 microcontroller. So MCU core would wake up, every 63 milliseconds to deal with this data. And the current consumption for this MCU core would be 51 microamps of current. So total is 66 microamps of current consumption. Now, if you use the logic which is running inside the sensor, machine learning core only consumes 4 microamps of current. Your microcontroller would wake up once every 30 seconds instead of every 63 milliseconds. So your microcontroller's current consumption goes down to 0.65 microamps. Add everything up, you have 20 microamps on this side. So more than 3 times power savings for the same algorithm that is running when it is running in the sensor. So main idea is algorithms such as activity recognition, they need to run all the time. To detect in bag versus out of bag, these algorithms need to run all the time. So always on kind of algorithms. So it makes sense to run that logic inside the sensor because it can implement this algorithm at very low current consumption. Here are some examples of algorithms that can be implemented inside a smartwatch. So human activity recognition, 6 microamps of current consumption. Gym activity recognition, another 6 microamps of current consumption. A wrist tilt, when you tilt your wrist, it should light up the display. So that algorithm can be implemented using a finite state machine. It'll take 16 microamps of current for the compute part. So you can go down the list and sleep detection, sleep mode, sleep state detection, 1 microamp of current consumption. So if you are building a smartwatch where your objective is that the battery in a smartwatch should last as long as possible, all of these different algorithms, you would want to run them inside the sensor rather than on a application processor or a microcontroller. So that is the main idea. So overall system efficiency will improve because you have distributed the compute inside the sensor as opposed to all of the compute on a microcontroller or an application processor. So now let's talk about the AutoML part. So there are, as we have 5 steps. So the AutoML part for this, first of all, why? What is the need for the AutoML part? First thing is that machine learning core inside the sensor is not a general purpose microcontroller. So it has many constraints. Number one constraint you already saw was there is a limited number of nodes that's available inside the sensor. Because if you make it a general purpose microcontroller, you would lose all the advantages of machine learning core. Your current consumption will increase. So if the logic sits in the gates and you are applying very simple logic, you're applying very simple features, mean, variance, you don't need a general purpose microcontroller to compute variance. You can put that logic in the gates. So that's what the advantage of machine learning core and finite state machine is. That you have limited set of features. You can apply only limited filters. And the window size that you operate on is also limited. The number of nodes is limited. So that's why we put together a solution where if you have labeled data that is available, we can process that labeled data with the knowledge of these constraints. So that's basically the AutoML framework that now is available in MEMS Studio, which can be downloaded from st.com. It will select the best MLC parameters, and you can use that as a starting point if you want to develop your own solution. So how does this work? So this is a framework architecture. So essentially everything starts with labeled data. And the next step is to pick filters. So for that given labeled data, the classes that you have selected, you want to pick the filters. Filters would be, again, low pass, band pass, high pass. I'll show you a couple of slides, to see, how it makes sense. So there are 2 options. One is the basic and the other one is exhaustive. Next step is to determine the window length, for algorithm. The third one is the features. If you know these 4 things, then you can generate a decision tree. You can feed that to Weka. You can provide that to libraries that are available for Python. You can use MATLAB, or you can feed that to ST's algorithm. It'll generate a decision tree for you. So for automatic feature selection, there's an ensemble of methods that we have: random forest, ANOVA, AdaBoost. sequential and recursive feature elimination, feature addition. So those will be all available to try this out. So once the decision tree from this algorithm is generated along with the statistics, essentially next step is to generate the chunk of code which will be downloaded into the sensor. So, for filters, here is the expression for the filter. In this transfer function, as I was saying earlier, all you need to determine are these coefficients, A's and B's and the gain. So with that, you can put together a second order IIR filter, and you can apply that filter to any of these axes. You can have multiple filters, you can choose combination of them. So there are two algorithms. So I'm using the example of human activity recognition here. So what you see here is a frequency spectrum. Stationary, walking, fast walking, jogging, and biking are shown in different colors. So you can see the biggest peak is the one that corresponds to jogging. And the number that corresponds to the lowest frequency is that for walking. So based on this, the automatic filter selection algorithm will identify the maximum of signal in this frequency spectrum and then pick the right filter. The exhaustive search algorithm essentially uses this entropy. The mechanism of, so what you would want to do is, minimize the entropy against, for a selected class. So you will pick each of these classes, walking, running, jogging, biking, and then compute the entropy. The filter that minimizes the entropy, for a given class with respect to all the other classes is the right filter for that class. So that's how the exhaustive search will work. So as you can imagine, exhaustive search will have a lot more compute. Now, these pieces that I'm talking to you about, the AutoML, that does not run inside the sensor. That runs on your laptop or your cloud. And the reason is fairly simple, that you need to have large archive of data that needs to be processed. So this logic will run either on your laptop or in cloud. Now the second thing is window size. So as I was saying earlier, a decision tree needs to operate on a certain window of data. In machine learning code, you can go from 1 to 255 sample window size. So how do you determine this? So I'll just, again, take that same power spectrum for human activity recognition. Stationary, walking, fast walking, jogging, and biking. So in this case, you look at the first significant peak in the power spectrum. So this data was recorded at 30 hertz. So the first peak is at 1.8 hertz. So you take that number, you reduce the frequency by half, so 0.9 hertz, invert it to get 1.1 second as the time period, multiply that by a factor of 2, so 2.2 seconds, and then multiply that by your sample rate, so 30 hertz. So 67 sample is your window size. If you provide label data to AutoML algorithm, it will automatically determine the window size for you. And the concept is what I was just trying to describe to you. It uses this kind of a concept. The last stage is automatically determining the features that you need to use. So machine learning core supports 31 features: mean, variance, energy, peak to peak, maxima, minima. And then there are features such as zero crossing and number of peaks, both with positive and negative zero crossing, positive and negative number of peaks. So last 6 of these features are threshold features. So you have configurable thresholds. You can decide what is your zero crossing. So how do you do the feature selection? So you have an ensemble of methods that are available. And these methods are ANOVA, AdaBoost, random forest, sequential feature addition, and recursive feature elimination. So the features that have thresholds, they are optimized by picking the range of candidate thresholds and calculating the highest accuracy through cross-validation for that given data set. So that's how you'll arrive at what is your feature to pick in this ensemble. The other important thing to point out is that you can configure the algorithm to pick n number of features. You can say, okay, I don't want my decision to be too large. So you can reduce the number of features. Maximum is 31. So you can reduce it to, let's say, I can pick only 10 features or 5 features, whatever it may be. And lastly, this approach will remove cross correlation from all features if the correlation value does not exceed 0.8. So the main idea here is that you don't want this to make sure that there is no overfitting. Otherwise, your label data has this issue. So, we tested this for a variety of data sets, and there's a paper that has been published in IEEE sensors letters. So, all the details are available in that. We picked this data set, publicly available data set called as Auritus. It has 9 activity classes, such as walking, jogging, jumping, lying down, standing, turning left, turning right, falling. And this data set was collected with help of 45 participants with a ear-worn device. Sensor sample rate was 100 hertz, so it is about 2.7 hours of data. So a decent sized data set. And our search space included decision tree for machine learning core, random forest, which can be implemented onto a microcontroller, XGBoost, which can be implemented on a smartphone, or light GBM, gradient boost method for a smartphone. So when we look at the performance, what we found was the decision tree, achieved the best results, for this particular data set. 93% absolute accuracy with 1 milliwatt of power consumption, current consumption. So it outperformed the other classifiers that I talked about by 7 to 21%. Runtime, as you can imagine, decision tree is a fairly simple implementation. So the runtime for decision tree was 45 times to 2,400 times less than other classifiers. And the accuracy was higher. So when you compare the accuracy with random forest, XGBoost, and light GBM, 35% higher than any of these other classifiers. Current consumption. So we already did the math. You saw the math when it comes to microcontroller versus machine learning core. So for a smartphone or an ARM Cortex-M4 implementation, 41 times to 137 times lower current consumption when you implement this in machine learning core versus algorithms implemented otherwise on Cortex-M4. Now let me switch gears. So we talked about sensors with machine learning core. We know that it has its own limitations. Its limitations, are, you only can work with certain features. You have only a certain number of nodes that are available, and you can only deal with 8 decision trees at max. So to overcome that, we have a new paradigm, which is this intelligent sensor processing unit. So this particular implementation will allow you to run your C code on the sensor. So if you can run your C code, essentially you can implement a BNN, binary neural network, on the sensor. Remember, this is not a Cortex-M0 or a microcontroller that goes inside this. It's a very simpler version of this. So what we have is a STRED architecture. This is an ST proprietary architecture. ISPU is based on that. And it essentially has a 32-bit RISC Harvard architecture, 2 different clock speeds that are available, 5 megahertz and 10 megahertz. It has a minimal floating point unit that's available to you. It has 2 RAMs, 32 kilobyte RAM for code and read-only data, and 8 kilobyte of RAM for variable data. So in order to make this sensor, number one, efficient in terms of current consumption. Number 2, cost-wise, it has to be meaningful, right? If I put everything into it, then commercially it will not be accepted. So it does not have any onboard non-volatile memory. So the disadvantage is that every time you start up the sensor, you have to download the code into this again at the time, what you do at the time of initialization. This is the only drawback. However, what it offers to you is the capability where you have accelerometer, gyroscope available to you, but at the same time, you can bring in external sensors like a magnetic sensor or a pressure sensor, time of flight sensor, over the I2C bus, auxiliary interface of an I2C bus. So there is a bank of registers that essentially will be used to bring in the sensor data over the serial interface bus. And there's another bank of registers that will generate the output, and you can read the output from those registers. You can run up to 30 algorithms at the same time. And the way you would interact with your application processor or a microcontroller would be through interrupts. So interrupt is generated, you can go read the output registers and see, okay, I have this output for this algorithm. So biggest advantage are ultra low power consumption, very low latency. Everything is processed on the sensor, easily programmable because you can write everything in C and download onto this. So the AutoML logic I talked to you about, where for label data you generate a decision tree. Now that decision tree, you can take it and implement that as C code. Put this onto ISPU, you can process it. Some customers say that data privacy and security are really important to us. So we want all the logic to be on the sensor. So it satisfies that. And this particular sensor has pin-to-pin compatibility with all our IMUs. So customers who are building solutions with our IMUs, they can easily replace that by maintaining pin-to-pin compatibility. There are different evaluation tools that are available for all our sensors, machine learning core as well as ISPU. So sensors are available on a DIL24 adapter board, which can plug on to a board such as this one, which connects to your laptop. And MEMS Studio will allow you to configure the sensor, allow you to collect the data, allow you to modify any of the settings on the sensor, all of that. Even download your machine learning algorithm into the sensor. You can do data injection to the data that you've collected in the field. If you want to debug your logic, you can do that. Then we have this ecosystem called as Nucleo, where you can stack your shields. So you can select your microcontroller and put a shield corresponding to the sensors, and these sensors will fit onto that shield. So you have the capability with machine learning core or ISPU, and with MEMS Studio you can interface with all of this infrastructure. So the development flow essentially is shown on this particular slide. So main idea is, if you are trying to generate a BNN or any neural network which you want to implement onto ISPU, you can start with TensorFlow, Keras, QKeras, any of your favorite tools. Generate your neural network, convert that into C code. Then you have essentially that C code has to run on ISPU. So this particular tool chain through ISPU gen utility will create that into the needed SREC file, which then becomes part of your header file that can then go on to your into your firmware for the application processor. So this tool chain is available for anybody to try. It can be downloaded from sc.com. It has this tool chain will give you your C, C++ compiler, assembler, linker, and a bunch of libraries that you can play with. And this is available for the 3 most commonly used platform, Mac, Linux, and Windows. This is also available as a plugin into your Eclipse IDE, which basically will look very familiar to you if you are using Eclipse for your development. And then there is another flavor where you have a firmware package for sensors with ISPU. So here, the biggest advantage is that you get your low-level drivers, you get your libraries, you get even a firmware implementation that you can play with, which will allow you to really quickly put your algorithm together and maybe even integrate some of the libraries that are already available on st.com, like accelerometer or gyroscope or magnetometer calibration libraries, sensor fusion, activity recognition, your pedometer, your wrist tilt, fall down, those kind of applications. And this particular Xcube ISPU, this package, it is compatible with our Nucleo ecosystem, along with the boards that I was showing you on 2 slides that earlier. So a whole variety of libraries are available on GitHub for ISPU to try. Calibration libraries, sensor fusion libraries, some of the features for variables like wrist tilt, activity recognition, pedometer. For industrial, anomaly detection, vibration severity, sliding DFT, you can apply that. So that brings me to the last slide here, the summary. What I have talked to you about is now a capability of running your AI logic on sensors. And this will improve your system efficiency and power and features such as current consumption, latency, and it will even address aspects such as privacy and security. There are very wide variety of applications that can be implemented using this paradigm and using these sensors. So, there are applications that people have put together for consumer devices. So I talked to you about the laptop. There are a bunch of customers that have put together these solutions for smartwatches, hearables, in automotive, in a car. There are applications in industrial domain as well. So machine learning core and finite state machine and ISPU, they will allow you to put together a solution that improves overall system efficiency. Rather than dealing with raw sensor data, you would deal with output generated by the sensor. And the AutoML tool that I talked about, can help you put all your solution together, where you do not need to do feature engineering, or you do not need to, dive into, signal processing where you need to figure out what filter to use for this data. So that's all I have. I can take a few questions now.
Questions?
Please.
I'm curious, you outlined various activities that can be recognized by the developer, the laptop on the table, laptop triangulating. I'm curious, is there a way to benchmark the accuracy or the confidence of these predictions it makes? Now, I guess like for maybe more medical applications, right? The confidence interval what's happening. Yeah. How do you guys benchmark that?
So this AutoML tool that we have, when it generates a decision tree, it will give you absolute accuracy over the entire data set that has been provided. You can choose for the given data set, you can separate your training and test data sets. So thereby, you would not mix, what your algorithm has been trained with. You would use a different data set to test your performance with. So it will essentially, n-fold validation kind of methods are available in the AutoML tool for you to try. This tool will give you, you can also configure the tool to give you different options where, you control the number of features, by selecting, let's say I want to give it the best, you can pick all the features versus give me the features for the lowest possible power consumption, but, above a certain accuracy. It'll give you all these combinations. So you can, collect all of this such information for your labeled data sets that you have, used for, in this AutoML implementation and arrive at, an ensemble of results, which will allow you to pick, best possible implementation and also compare that against any other data set that you want to work with. So, for, inertial sensor data, magnetic sensor data, there are lots of publicly available data sets, which like for human activity recognition, there are many, many data sets that are available, some that are really extensive. We have put together, a human fall detection algorithm. It essentially has 147 classes, 147 activity modes, which would include everything from walking, running, jogging to vacuuming, washing dishes, any of the human activity modes. So for all such, classes, you can actually process them through this data set, figure out, how well is your algorithm working. The next part of this, when you're trying to build an application, let's say, where you want to say, okay, I want to use, gait analysis or whatever for medical applications. You can further, take real-time data, record that on our devices such as sensor tile, bring this data back and, through real-time data injection into the sensor, in this case, you're exercising only the machine learning core block or the finite state machine block. You can do your hardware in the loop simulation. So you can see how well is the solution working. So all of those are possible ways of establishing the performance of algorithm plus this sensing block plus this compute block.
Okay, we have time for just one or two more questions.
Please.
Yeah, very nice work. Actually, I have a question about the applications area. So I wonder, is there a statistics on how many percent of energy inside the whole system it consumes with or without the sensor processing?
Yeah. So, I was sharing with you, this particular comparison. If you consider this use case scenario, let me just go back a few slides here. And I think it's this slide. Yeah. So in this particular slide, use on one hand, you see compute that is done by, implementation using a microcontroller. So this is a use case scenario where, you have your Cortex M0, or rather Cortex M4 in this case, waking up every 63 milliseconds to process the sensor data. And your sensor is, consuming 15 microns of current consumption. So you can do a comparison between the two. So when the logic is implemented in the machine learning core, it consumes 20 microns of current as opposed to 66 microns of current for the same exact feature. So such, comparison can be done. Our tools allow you to, measure the current consumption for each solution that has been put together.
Okay, one last question.
Thank you for your amazing talk. So I'm very curious about the specific classification in models. So as you know, there are so many activities going online. And when you define specific classes, there should be always some activities outside of your defining
Yes.
types. So I'm wondering how do you sort that? What's the strategy? What's the strategy you use to resolve this problem? Is that model establishment or some data set processing? So maybe use some heading strategy to help the data set, or I'm not sure. So if you just
Yes. So, you're defining your classes. I'll use the human activity recognition example to answer this question. So human activity recognition would have, walking, jogging, bicycling, climbing up the stairs, climbing down the stairs, elevator, escalator, all these classes you can define. So you can collect data for all of these classes and you can say, okay, here is my label data for all these classes. When you design your algorithm, you can also have one of these classes which says none of the above. So it's your catch-all class. So what that means is that, whatever is your activity mode, if it is not recognized, it should fall in this none of the above class. And thereby, you can say, okay, I can achieve 95% accuracy for walking. I can achieve 98% accuracy for jogging. I can achieve for this given data set. You'll see the statistics when you process this using the tools such as MEMS Studio. And then you'll say, okay, if you pick the none of the above class, 10% of my data falls in none of the above, which means my model, is actually picking up something which was not classified by any of these other classes.
We have to cut it off now. Sorry, we have to get him to lunch before they close the kitchen. So let's thank our speaker again.